Well, here we have a growth problem involving an exponential function. So, a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100 e to the 0.045 t, where n is measured in grams and t is measured in days. So we'll do A and determine the initial amount of bacteria. Well, initial corresponds to t equaling 0 times 0. So we have n of whatever equals 100 e to the 0.045, and in place of the t we'll put parentheses. Now if we put a 0 here, we must put a 0 there. So that's going to be 100 e, and 0 times 0.045 is 0. And so 100, and e to the 0 is 1, and 1 times 100 is 100. So n of 0, the initial amount, is 100. Now we have to find B, the growth rate of the bacteria. Well, this function in general can be written as n of t equals n sub aught, the initial amount, e to the rt, where t is time and r stands for rate. So t corresponds to time and r corresponds to rate. So our function is n of t equals 100 e to the 0.045 t. Well, whatever is in the r position is the rate. That is, whatever the coefficient on t is the rate. So the coefficient on t is 0.045, so r equals 0.045, or in terms of percentage, 4.5%. But we'll use the decimal in our calculations. So for C, we have to determine the population after 5 days. So t equals 5 days. So we have n of whatever equals 100 e to the 0.045, and in place of t I'll install parentheses. So if we put a 5 in this set of parentheses, we must put 5 here. And when we run this calculation through our calculator, we wind up with 125.232, and this thing goes on forever. And that's the number of bacteria, but this equals approximately, we'll round down to the nearest whole bacteria, and so we have 125 bacteria. Good. Now for D, we have to know how long it will take the population to reach 140 grams. Well, we know this, the population is n of t, and that's got to equal 140 grams. So 100 e to the 0.045 t must then equal 140. Dividing both sides by 100, we have e to the 0.045 t equals 140 divided by 100. Now if I move this decimal to the left twice, I must move this one to the left twice. And we have e to the 0.045 t equals 1.4. And now we'll rewrite this in logarithmic form. So the base is e. So we'll use the natural log symbol that implies that the base is e, and the result is 1.4, and the exponent is 0.045t. Now we must isolate t. To do that, we'll divide both sides by 0.045. So t equals ln of 1.4 divided by 0.045. And when you install those values into your calculator, you wind up with approximately 4.8, and those are years. Yes. The final question, E, asks, what is the doubling time for the population? So, if we double the initial value, the initial value is 100, if we double that, we get 200. So 200 equals 100 e to the 0.045 t. Now let's divide both sides by 100, and when we carry out that division, we wind up with 2 equals e to the 0.045 t. Now we'll rewrite this in logarithmic form. And so the base is e, so log to the base e, or the natural log, and the result is 2, and the exponent is 0.045t. So isolating t, will divide both sides by 0.045. So t equals ln of 2 divided by 0.045. And when we install these values into a calculator and round, we get approximately 15.4 years. Good, we've got it.